Okay, good. And now, how about the variance of this y, right? Don't forget, this y is nothing more than a linear combination or a linear transformation of x, right? And now the variance of y. Maybe we denote that sigma squared. We can subscript it with a y if we want, okay? And this particular one is a little bit easier to just kind of keep it in terms of the definition, right? That's going to be the expected value of y minus the mean of y quantity squared. Right? Reason why it's easier to keep it in this form right here is because we know what y is. We also know what the mean of y is, right? So this one here is kind of interesting because we don't have to do much of any work, right? It's ax plus b, that's what y is, minus a mu sub x plus b, close it, square it. It's all in the expected value. Right. Interesting. Let's see. What do we notice here? First thing I notice is those b's cancel out. We in agreement? Those b's cancel out? I agree with that. Those b's cancel out. And I can write that as the expected value of, how can I write that? I can factor an a out. A squared x minus mu sub x squared. You agree with that sentence right there, right? Now, somewhere toward the bottom, I've got here the expected value function distributes through sums, differences, and constant multipliers, which means that I can factor that a squared out to the front. Right? It's just a scalar multiplier. Is a squared the expected value of x minus mu sub x squared, right? And this here is simply the variance of x. So the variance of y is a squared times the variance of x. Interesting. Right? Well, why is that? Look at that. And so, first off, in the variance of y, I see that the b's disappeared. Can you argue with me one way or the other why those b's disappear? Apparently, don't forget what variance is. It's a measure of variation. Right? What role in a linear transformation like this? What role does the a have?
Scalar.
It's a scalar, which means it scales, right? Which means it spreads out or it contracts. Does that affect variation?
No.
Yeah.
Yes.
Yeah. What role does the b have?
It shifts.
It shifts, right? So does the shifting affect variation?
No.
Oh, that's right.
Do you see what I'm saying here? Right? Do you see that this x taking on values 0, 1, and 2 with probabilities, I don't care, whatever, 0.1, 0.3, and 0.6, and this this random variable, W, PW of W, takes on
2, 3, 4.
200, 201, 202 with probabilities 0.1, 0.3, and 0.6, right? Right? Do you see that this is just picking this up and placing it in a new place? Do you see that the amount of variation within that set is the same as it is within that? They just happen to be in different locations on the number line, right? Right? And so that's a reasonable argument for why that B disappears from that expression, right? Right? Whereas the A is rescaling those, right? Right? By the way, on here, let me summarize. Okay, so y equals ax plus b. We've seen that the mean of y is a times the mean of x plus b, right? It takes that scale, takes that shift into account. The variance of y is simply a squared times the variance of x, right? By the way, I didn't add it there, but the standard deviation of y is the square root of a squared sigma squared of x, which is the absolute value of x times the standard deviation of x. Right? More to the story, by the way. As long as that a is not 0, this is a 1-to-1 function, isn't it? It's a 1-to-1 correspondence, right? Right? And so notice this. What is also of note? Notice. What is the probability mass function of y? I bet we can deduce that. Well, that is the probability that y is equal to little y. We in agreement with that statement? Probability mass function is the probability at that point for a discrete random variable, right? And y is ax plus b. So that's the probability that ax plus b is equal to y, right? Which is the probability that x is equal to y minus b over a. Am I right about that? Did I solve that correctly? For x, right? And that is px of y minus b over a. See what I'm saying there? Right? For instance, I should have started with a less silly example at the start of class, but we're going to carry that same silly example all the way through our day, right? And so we've got x can take on values 0, 1, and 2 with probabilities, what was it, 0.1, 0.3, 0.6. We saw that the mean of x was 1.5. We saw that the variance of x was 0.45 if memory serves, right? If we said y is equal to, it really doesn't matter, 10 minus 4x, well, then the mean of this y is 10 minus 4 times the mean of x. Am I right about that? Right, there it is right there, right? Which is 10 minus 4 times 1.5, which is 3, which is 6, which looks to me like about a 4.0. Does that look about right? Did I do that right? Okay. And the variance of y is what is the variance of y? How can it, what would the variance of y be? Negative 4 squared times the variance of x. Yes, yes, is negative 4 squared times the variance of x, or 16 times 4.45, 16 times 0.45, and I get something around a 7.2. And so here's the thing. Here's the thing, right? When x equals 0, then y equals 10, right? And so isn't the probability that y is 10 equal to the probability that x is 0? Make sense? Right? By the way, is that what I'm saying over here? I think it is. Right? Note on the previous page. Note from previous page. Right? The probability that y is equal to 10 is the probability that what is y? 10 minus 4x is equal to 10, right? Is the probability that minus 4x is equal to 0 is the probability x is equal to 0. You see what I'm saying there? Right? Similarly, when x is equal to 1, then y is equal to 6, right? So py of 6 looks like it should be px of 1, right? And x is equal to 2 is y is equal to 2, so py of 2 must, oh, is that really right, is equal to px of 2, right? So the probability distribution of y is, y can take on values, what can they take on? 2, 6, or 10, with probabilities 0.6, 0.3, and 0.1.
And then we see that 4 drop out.
Do you see what I'm saying there? Does that make sense? Right? And then you can convince yourselves, note from this perspective, that the mean of y is the sum across all your y's of y times its weight, or 2 times 0.6 plus 6 times 0.3 plus 10 times 0.1. Right, what's that come out to? That looks like a 1.2 plus 1.8 plus 1. Is that what that looks like to you? 4.0, and that's what we got when we did it our first way. You see what I mean there? Right? You can confirm the variance probably just as well. How's that feel? You know? Now this particular example right here, you know? It's a linear function. By the way, we talk about linear functions all the time in this course, you know? For instance, you know, you take a sample average. Well, isn't that, I have a data set of values, I want the average of them, don't I add them all up and divide by how many I have? Isn't that a linear combination? You see what I mean? And that could be written in this kind of a form, okay? And so, fantastic. In a more general sense, okay, more general sense, okay, if y is some function of x, right? In a discrete case, x is discrete. Py of y, right, is the sum. Let's see, is there a shorter way I can write that? Probability-wise, let me just write to it. Probability y is equal to y. Probability h of x is equal to y. Probability h of x is equal to y is the sum of the probabilities of x. What am I summing over? All x such that h of x is equal to y. What I mean by that, okay, is suppose x has the probability distribution, okay, that x can take on, oh, I don't know, maybe I'll do it this way, x, px of x, maybe it can take on values -2, -1, 0, 1, 2, and 3, okay? Oh, with probabilities, oh, I don't know, 0.35, 0.2, 0.2, am I up to 75, 0.1, 0.1, what am I up to, 95, 0.05, did I produce a valid probability? 4, 6, 8, 10, that works, right? Higher level math, is that adds up to 1, doesn't it? Okay. And you know, what if I do something, see that linear combination is sweet, right? Because there's a one-to-one correspondence, but let y be equal to the absolute value of x, find the probability distribution of y. Now, so first off, what values can y take on? If x is discrete and y is the absolute value of x, is y discrete? Is there a, how many, what values can y take on with non-zero probability? All of them? 20?
Oh. 6.
I could take on 0, 1, 2, and 3.
0, 1, 2, and 3. Okay, so.
So why is that?
Well, that makes it discrete. 0, 1, 2, or 3. That's a finite list, right? So y can be values 0, 1, 2, or 3. Are we in agreement with that? Right? So, Y can be a 0, 1, 2, or 3. Okay? So what are these probabilities? What's the probability that Y is 0? 0.35. 0.35. Saying, by the way, I'm off the screen again, sorry about that. Right? Is Px of 0 or 0.35, okay? Now the point here, what's the probability that Y is 1?
0.4.
Do we all see a 0.4 there that we're looking through? That's what this notation, wherever that notation is hiding up there toward the top, right? When you don't have something that's linear, when you have something where you might have repeat values, the probability of Y is the sum of the probabilities across X so that X maps to that Y, right? So do you see that the probability Y is 1 is Px of -1 plus Px of +1 or 0.4? You in agreement there? You see where that's coming? Probability Y is 2 is Px of -2 plus Px of +2. Oh wait, yes. Yeah, which looks like a 0.2. And the probability that Y is 3, well, you see again, there's only one X value that maps to a Y of 3. So that would be a Px of 3, and there is my remaining 0.05. Theoretically, I've got another valid probability. It needs to add up to 1, of course. Right. How's that feel? Does that seem okay, please?
So let's say, because right now we have the absolute value of x.
Mm-hmm.
If this was something like x squared,
Mm-hmm.
would because the probability that y is 1 would be x is -1 or y is 1.
Right.
But then the probability that y is 4 would be -2 and +2.
That's 100% right.
Okay.
100% right. Yeah. Good. Very nice. You know, like if you think about it, x is a displacement vector. You know, a direction, a distance in a particular direction, and y is distance. You know, something like that. Yeah. Very nice. How's that all feel? Seem good for us? Okay, we're doing a good job here today. Okay. And so, that's kind of an overview of discrete random variables. Like I said, we would talk about kind of 2.1 through whatever it is, 2.4, kind of this overview in general. Then we would go back to 2.1 and talk about some specific cases, right? And so now some specific discrete random variables. Right. And by the way, let me paraphrase this by a little paragraph I copied out of another book. By the way, you know, in Canvas, I have been posting extra kind of practice documents. They're coming from that DeVore textbook. And I hope you find those helpful if you look at them. Hopefully, you know, I do know that when I write exam and homework questions, kind of the level of them are a little more aligned with what you see in that DeVore book, okay? And so I thought that would be kind of the closest thing to good practice besides the practice exam itself. And so copying out of that book, let f of x be a probability function. For a random variable, call it x. Okay. And suppose that this f of x depends on some quantity that can take on a bunch of different values. Of values. That quantity is called a parameter. That quantity is called a parameter. Okay? And the collection of all probability distributions, probability distributions, okay, for all the values of this parameter, values of this parameter is simply called a family of distributions. For instance, you've heard me maybe mutter out the side of my mouth things like binomial distribution. Well, that's a family of distributions. The geometric distribution is a family of distributions, you know? And the parameters uniquely define what the particular member of that family, okay? And so that's what we're starting to talk about to kind of classify these big picture things, okay? And the first one is simply the easiest one, okay, one we generally start with, and it's called a Bernoulli. A Bernoulli random variable. Okay? And a Bernoulli random variable, okay, is we have an experiment that we run one time, so it's a single trial, okay, and it can either result in a success, event A occurs, that event A occurs, or a failure. Event not A occurs. Okay? And then the random variable x is coded as x is equal to 0 for a failure and 1 for a success. Right? The probability and for this experiment, the probability of a success is denoted P. Okay, and I'll say thus the probability of a failure is 1 minus P, often written as Q. Okay? So this is a random variable. It's coded either 0 or 1. 0 is we run the experiment and we get a failure, event A does not happen, or it's a 1, okay? Now, so for instance, we've been doing these since day 1, right? And so such a random variable, okay, random variable is called Bernoulli. Bernoulli random variable. Okay. It has one parameter, and that parameter that you need, that completely defines this experiment, is P. Right? We might write random variable X has the distribution that it's a Bernoulli with parameter P. Right? For instance, you know how we do in here. For instance, flip a fair coin, right? A success is defined as it lands on heads. So if it lands on heads, we say X is equal to 1. If it lands on tails, we say X is equal to 0, right? X equals 0 means lands on heads. On tails, say that right. X equals 1, lands on heads, right? This X is a Bernoulli with parameter 0.5, right? So and similarly, we roll a 6-sided dice, let a success be it lands on 6. Well, then X is a Bernoulli with a parameter 1/6, right? Does that make sense?
Okay, so you can take, just because it doesn't have to have exactly 2 outcomes, you can still read
It has to have, well, it has to be classified as having 2 outcomes, right?
You can draw your boundaries, so even if there's the possibility of multiple outcomes.
You have A and you have A complement.
Yes, but like with the 6-sided dice.
You have A and A
Yeah.
complement. What is A complement? All those other choices, right? And so, yes. And so, not to, you see exactly what I'm saying there? Right. And so similarly, I don't know if I should write that down, right? Roll a 6-sided dice, right? Define a success as the dice lands on a 6, right? This Bernoulli X is going to be P is 1/6, right? And so, right? Makes sense? And by the way, you could define it differently, okay? And so, let this random variable X be a Bernoulli with parameter P, okay? Then its probability distribution is either a 0 or a 1 with probabilities. Probability it's 1 is P. Probability it's 0 is 1 minus P, often denoted as a Q. Okay? Q plus P have to add up to 1. Right? The mean of this random variable is, excuse me, don't forget the sum across all the x's, right? Going from 0 to 1 of x times its weight, namely, somewhat trivially, 0 times q plus 1 times p, or p. So the mean of such a distribution is simply p. Right? The expected value of x squared is the sum of the x squareds times its weight, but trivially it's just a 0 or a 1, is 0 squared times q plus 1 squared times p, which is p. So the variance of this is the expected value of x squared minus the mean of x squared. There's that shortcut form right there, is p minus p squared, right? Which is p times 1 minus p, which is p times q. You see, you kind of see that argument there, right? And don't forget, what does this thing? Well, I don't know what p and q are, right? But this random variable x is either a 0 with probability q, 0, or it's a 1 with probability p. Plus q equals 1, right? And where is the mean of that? Well, the mean of that is going to be right at p. Okay? How's that feel? Does that seem okay? Let's see. And then we've got a couple more of these that grow out of this Bernoulli. Okay? And the following, well, what can I do in 5 minutes? The distributions, the binomial and geometric distributions are what?
What's back?
Projector.
Yeah,
It's doing that. We might have to do a little experiment on this. See? That blip, right? Happening randomly and independently in time, right? It's a discrete random variable. How many blips are there in a minute?
16.
Did you count them?
No.
16 of them, right? But there aren't 1.5 in a minute, and there's not -3. It's the number of blips in a given amount of time is a discrete random variable, right? If things are occurring randomly and independently in time, it follows a model called a Poisson random variable. It's the third one we're going to talk about after we're done these next couple. So by next class, we'll be talking about these. We'll all be like counting these blips so we can try to model this. Yes. Anyways, before we get to the lovely Poisson, binomial and geometric distributions are both stem out of this notion of a Bernoulli. But what we want to do is we want to have repeated, identical, independent trials. All right? Are built from the Bernoulli. Where we have had repeated independent, identical trials, right? So the first one, I don't have too much time. Maybe I can simply just list it. The binomial experiment. Is we have a fixed number of trials. We have n trials. Right? N is fixed. Okay? Should be predetermined and fixed. I always tell I shouldn't tell the story. We don't have time for that. Okay? The trials are identical and independent. Okay. Each trial results in either a success or a failure. Okay? Okay? For each trial. By the way, the trials are independent and identical, so what I'm about to write strikes me as redundant, but for each trial, the probability of a success is a constant, trial to trial to trial, and we'll call it P, right? The probability of a success is constant. Call it P. Okay? The probability of a failure is also, of course, is constant. The probability of a failure is 1 minus P, often denoted as Q for shorthand. Anything else I should say there? I should introduce a random variable. Random variable X. Random variable X counts successes. Okay? For instance, every single one of those questions, when I said things like, flip a coin 10 times, what's the probability it lands on heads 7 times? That was a binomial. Roll a dice, right, 5 times. What's the probability it lands on 6 twice? That's a binomial. You see what I mean there? You know, randomly select 100 people. You know, what's the probability that 82 of them are right-handed? That's a binomial. Yes?
So I guess what I'm kind of confused by is, in this case, would X kind of be considered the number of branches in those scenarios?
It would be the number of successes along the branches.
Okay.
Right? 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 Such a random variable, and don't forget that random variable X counts successes. That's what makes it a binomial, right? By the way, in a minute, well, in a minute plus 48 hours, we'll say, let's let random Y be the number of trials until the first success. That's a whole different model. That's the geometric. Do you see what I mean here? So, such a binomial follows these conditions right here, has 2 parameters, right? A binomial random variable, the probability function is completely defined by 2 traits. What is n, the number of trials? What is p, the probability of success? Okay? X is a binomial random variable. Okay? And a binomial has 2 parameters, namely n and p, right? So we might write X is binomial with parameters n and p, right? That tilde means has the distribution, okay? So, we're out of time here. So next class, we'll add the probability function. We'll add, which by the way you already know, but we'll add the probability function, the mean and the variance to this, and talk about the binomial. To discuss more next class. Stay tuned. Have a great couple days.